Hi everyone. In this video, we're going to introduce some derivatives and antiderivatives relating to inverse trig functions. Let's start with the derivative of arc sine x. It turns out that the derivative is 1 over root 1 minus x squared, which surprisingly isn't a trig function at all. But why is this true? Let's prove it. We start with y equals arc sine of x, and our task here is to differentiate this function. The problem is that we don't know how to differentiate arc sine, so it would be ideal if we could somehow eliminate arc sine from this equation. But we can do that by applying sine to both sides, because then on the right-hand side, sine would cancel with arc sine and leave us with just an x there. Now arc sine is gone from this equation, so we now know how to take the derivative of this expression, but we need to do it implicitly since the y is no longer by itself. That's no problem. Pause and check for yourself that these are the results of implicit differentiation here. And remember that the goal of this problem is to solve for dy over dx, but that's now easily accomplished by dividing the cos of y over to the right-hand side. So this here is the derivative we wanted, but currently it's expressed in terms of y, where we want it expressed in terms of x. In order to accomplish that, I'm going to apply the trig identity cos squared plus sine squared equals 1. For the moment, just trust me that this is a good idea, and you'll see the reason why in just a moment. Let's rearrange this identity to see what cos of y is equal to. Just don't forget to include the plus or minus when you take the square roots. Now, here's the reason why this identity is useful. Earlier on, we saw that sine of y is the same thing as x. So if we make use of that, we can see that cos of y is actually equal to plus or minus root of 1 minus x squared. So all I did is I replaced sine of y by x, since that's what sine of y is equal to. So plugging this in for our cos of y in our derivative formula, we get really close to the formula that I proposed earlier, but we do need to get rid of the pesky plus or minus sign. The key to doing that is to make use of the domain restrictions that were used to define the arc sine function. Since y is equal to arc sine of x, we know that y represents an angle which is in quadrant 1 or 4. So we know the cosine of that angle must be a positive value according to the cast rule. Anytime you take the cosine of an angle in quadrant 1 or 4, the result must be positive. And for that reason, we can see that when we say what cos of y is equal to, we're safe to reject the negative possibility. So we can drop the plus or minus sign here and get the formula we wanted, which completes the proof. When you look back, this proof really just boils down to using what we already know about the derivative of sine to figure out the derivative of arc sine, which is very much like what we did with logarithms and exponentials. And the same can be done really anytime you're dealing with inverse functions in general. As always, as soon as we know how to find the derivative of arc sine of x, then we also know how to find the derivative of arc sine of u, where u represents something more than just an x. That would be 1 over root 1 minus u squared times the derivative of u according to the chain rule. And we now know a function whose derivative is 1 over root 1 minus u squared, giving us a new integral formula. That would be arc sine of u. So this formula actually allows us to handle a type of integral that wouldn't have been possible previously without having knowledge of arc sine. What you'll notice also is that 1 minus u squared represents what's often referred to as a difference of squares. The formula that I've given us here as written is a bit limiting since it requires us to specifically be dealing with 1 minus u squared. So it would be ideal if we had a formula that allows for a more general difference of squares, such as a squared minus u squared, rather than just 1 minus u squared. And it turns out there is a formula for that. It's just arc sine of u over a. The only requirement is that a represents a positive constant. If a isn't constant, then this formula isn't applicable. I recommend putting these four on your formula sheet now. This last formula I stated still needs proof, so let's do that. Starting with the integral that we've been given, we need to show that this is equal to arc sine of u over a. Keep in mind that we already proved the formula for the case where a equals 1, so we can make use of that in our proof. And in order to do that, we're going to factor out the a squared from our denominator. Because if we do that, then we can have a 1 there instead, which would allow us to make use of the formula that we already know. So pause and double check that this factoring I just did is correct, and when you're ready, let's proceed to the next step. Next, we're going to make use of the fact that when the items under the square root are being multiplied, then we can apply the root to each of those items separately. We know the root of a squared is just a, since a is a positive number, so our integral simplifies as you see here. Since a is a constant, we can also bring it out front and get it out of the way, and so this is what we're left with. And what you'll notice is that this does resemble the form 1 over root 1 minus w squared, provided that we think of u over a as w. And for that, it's necessary to perform a substitution. So we're going to let w equal u over a, and then we need to calculate dw, which is 1 over a du. The easiest way to see that is by recognizing a is just a constant. We can also see that 1 over a du appears in our integral, and that whole chunk can now just be called dw. And what results then is just the integral of 1 over root 1 minus w squared, and we've already proven that this is equal to arc sine of w plus c. As a final step, we remember that w was the same thing as u over a, and that completes our proof. I'll take this opportunity to point out that from this point forward, I suggest you make a habit of looking for differences of squares when calculating integrals. I would even go as far to say that together with looking for f prime over f structure will get you through 90% of the integral problems in this course. So be on the lookout for those two things, differences of squares and f prime over f. Let's try an example. You would have an impossibly hard time with this integral if you didn't think about it the right way. But the second you notice there's a difference of squares here, everything actually falls into place pretty easily. I could suggest rewriting the denominator in a way that emphasizes the difference of squares. And once you've done that, you can more clearly see that structure of a squared minus u squared here, where in this case, a would be 2 and u would be 3x. Just be careful. If we want to think of 3x as u, then it's necessary to actually perform a substitution and keep track of the impact this has on dx. So calculate du and use that to figure out what dx is equal to, as usual. And after doing that, we can now express our integral as 1 over root 2 squared minus u squared, and dx is now 1/3 du. This successfully expresses our integral in a way that exactly matches the formula I provided earlier. So we know the result of this must be arc sine of u over a, where in this case, a is 2. As a final step, put u back in terms of x and you're done. My guess is that looking for differences of squares is something you were probably not in the habit of doing before, so hopefully this example convinces you that it is something worth thinking about from now on. Having covered the calculus of arc sine, we still need to look at arctan and arc secant, but I'll save that discussion for the next video, so I'll see you next time.